Fantastic. So our next talk, when we're ready, is from Leonardo at TU Darmstadt on a topic which actually was very important during COVID. Lots of work was going on using molecular docking codes, looking for what would make the best vaccines to treat COVID. This is one of the reasons why vaccines were developed so quickly this time compared to previous vaccinations. So are you good to go?
Yes.
Excellent. Thank you. Leonardo, over to you.
Yeah, thanks. Thank you for the introduction and welcome to this presentation in which I'm going to talk about our experiences working with molecular docking code and migrating this from CUDA to SYCL. So my name is Leonardo Solis Vasquez. I work as a postdoctoral researcher at the Technical University of Darmstadt. And so I'm going to discuss our experiences with molecular docking specifically. So molecular docking is a key method in computer-aided drug design, and it simulates the close interaction between two molecules. And the idea of molecular docking is to find the poses, the binding poses of these two molecules that are energetically strong. So at the TU Darmstadt, we have been working on Autodock GPU, which is a parallel molecular docking application that we co-developed with our colleagues at the Scripps Research. And the original version was written in OpenCL, and the first paper of it was published at IWOCL 2017. And then some years after, the work has been extended to a journal, in the Journal of Chemical and Theory of Computing. So years later, this OpenCL version was ported to CUDA in order to run COVID-19 research on the Summit supercomputer. And Autodock GPU has a challenging code structure and has a high practical relevance. So we thought this is a promising case study for evaluating an automated migration from CUDA to SYCL. And for this purpose, we have used the DPC++ compatibility tool. So in this talk, I'm going to discuss two main points of our work. First one is the experience migrating Autodock GPU from CUDA to SYCL. And then I'm going to discuss the evaluation we made using this SYCL code on CPUs and GPUs. So our strategy was to use the CUDA version of Autodock GPU as an input of compatibility tool and to use as much as we can the output, which is the resulting SYCL code. And then we had to review this code and to manually modify it in order to complete the functionality. So compatibility tool migrates the code, but also adds some comments that we use as guidelines for code completion and performance tuning. So we encountered different cases during our migration, and then we classify them in two groups, one for functional correctness and the other one for performance optimization. So this is a summary of the most relevant cases regarding functional correctness, and I'm going to go more in details. So the first one is that of reductions, and in Autodock GPU, we use reductions in order to keep track of the number of score evaluations. So scores are a number we give to each of these molecular poses, and then we compare during the molecular docking process. And in the CUDA version of Autodock GPU, we implemented this as multi-line macros that perform shuffles. And when we use this, for example, we pass this through compatibility tool, we found that compatibility tool cannot migrate these shuffles correctly. And specifically, this is because of the first argument of the shuffles in CUDA that are not supported in the SYCL counterpart. But then analyzing this code closely, we realized that this reduction or migrating this does not require us to deal with the shuffles one by one, but instead we can reduce, or let's say we can transform this reduction code by using a SYCL built-in function, which is the reduce over group. And then as you can see on the left, there's this initial CUDA code that can be migrated into fewer lines using this built-in function. However, we had to deal with shuffles one by one, and this is the case, for example, in this also macro that deals with that uses CUDA threads to find a minimum score. And so in this case, again, compatibility tool cannot migrate correctly. It performs an incorrect variable substitution. And in this case, for example, we had to fix this incorrect variable use as masks. The mask argument of the shuffle in CUDA is not supported in the SYCL version. The case of synchronization is interesting because in Autodoc GPU, these two intrinsics, the thread fence and the sync threads, are called always one following the other. And in this case, compatibility tool leaves the thread fence call as it is, so it leaves that untouched, and it migrates the sync threads instead to a SYCL barrier. And so this transformation that compatibility tool made sense as the barrier ensures two things. The first one is that the memory space is consistent across all work items within a work group. That means it acts equivalently to a thread fence. And also it ensures that the work item within a work group reaches a barrier call and acting equivalently to a sync threads. So our actions based on this was to keep the tool migrated barrier and to migrate the thread fence call that was still in the SYCL code, and we migrate that as a no operation. So another case regarding functional correctness was that of memory layout for vector data types. Because in the CUDA version of Autodoc GPU, the host allocates memory using size, the call to size of, in this case, to flow 3 or to other vector operations, other vector types like in3. And the thing is that the device performs pointer arithmetic that relies on that memory allocation. Compatibility tool migrates correctly the flow 3 in CUDA to the flow 3 in SYCL. The thing is that there is a different number of bytes being allocated in each of these cases, 12 for the CUDA version, 16 for the SYCL one. And so the problem was that this difference in memory allocation led to incorrect score evaluations. And the reason was the memory corruption, overriding portions of shared memory. So we had to correct this manually. Basically, we had to explicitly propagate this, the size of the allocated memory based on SYCL flow 3, or in other cases, based on SYCL integer 3, and to use also the pointer to the corresponding SYCL accessor. Okay, so far I have discussed about the cases that we needed to address in order to achieve functional correctness in our migration. However, there are other cases that were migrated by compatibility tool and the program was running. However, we needed to manually tune them in order to increase performance. So the first case was that of atomics. And the thing is that compatibility tool made an assumption here in terms of the memory order, the memory scope, and the memory address. So respectively, it assumed that the order was acquire release, the scope was that of device, and the address space was global. And although those configurations are safe, they are not strictly required in all cases, like in the case of Autodoc GPU. So we thought, how about we use more relaxed configuration so that we can increase the performance. And so this is what we did. We manually modified these configurations. So instead of using an acquire release memory order, we specified a relaxed order instead. And also for the workgroup scope, we used instead of device scope, we use workgroup. And for the global address space, we use instead local. The case of barriers is similar, as compatibility tool also assumes that the address space is global, but in this case, we had to specify the local memory space as an argument to the barrier call. Finally, in order to improve the performance of Autodoc GPU, we had to take a look at the math functions that were translated So the thing is that the CUDA and OpenCL versions of Autodoc GPU take advantage of the reduced precision and math functions in the kernels. But this is, let's say, this is something we need to specify manually in the SYCL version. So we had to transform this, for example, square root calls to native square, also for the sine and cosine functions as well. Okay, so far I have discussed about the transformations and the manual tuning I had to make on the output of compatibility tool. And here comes the evaluation on CPUs and GPUs. So this is a summary of the experiments we performed on 3 different devices. So we have used a high-end CPU for this, in which we compared both the SYCL version and an OpenCL version running on the same CPU. On the second experiment, we ran our SYCL version versus the CUDA on an A100 GPU. And on the third experiment, we compared the performance on an Intel Max 1550, also known as Ponte Vecchio. And in this case, the Ponte Vecchio runs SYCL code versus an A100 running the CUDA version. So for our experiments, we have used the input molecules that anybody can find in the Autodoc GPU repository. And also here we are comparing 2 methods available in Autodoc GPU. So Autodoc GPU runs a genetic algorithm and a local search. And there are 2 alternative methods when it comes to the local search. One is the SolidWeds, that is the legacy method introduced in the 1990s. And the Ada Delta is something we worked in the year 2018 or so, and it achieves superior molecular predictions as well. So in this case, we're comparing the ratios between the SYCL and OpenCL version, and this is on the CPU. And those ratios below the horizontal line means that SYCL is faster than OpenCL. And as you can see, in all cases, SYCL is faster indeed. And this is due to optimization pipelines that are specific to SYCL, like the pre-Spear V optimizations, the inlining functions, the inlining heuristics, sorry, and etc. And the maximum speed up comparing these 2 versions was 1.2, and it happens for the molecule 1 STP. So here again, we're comparing the docking time ratios, this case between SYCL and CUDA on the A100 GPU. And for these cases, the horizontal line means, or those ratios above the line means that CUDA is faster than SYCL, with the exception of the case on the left, in which SYCL is barely faster than CUDA, 1.1 times faster. So in order to understand this, we profile executions of Autodoc GPU of both CUDA and SYCL on the A100 GPU using the Nsight compute tool. And we found that both CUDA and SYCL versions are compute bound. However, we think that SYCL is apparently performing more computations than CUDA based on the numbers we see in this chart. And we think that this is possibly due to a mismatch in the arithmetic precision used. Also, we have collected other measurements, and one of these is the number of theoretical warps, and SYCL actually can launch only half of those that CUDA can. Also, we found that the register pressure is higher in SYCL, almost double than CUDA the CUDA has, and this is, well, a problem because higher register pressure means lower kernel occupancy, and thus SYCL reaches lower performance. And we thought of how to limit the number of registers that can be allocated per thread, and we found that we could use some compiler options like the max rec count that we can pass down to the underlying compiler to limit this. We're going to try this also. So finally, this is a comparison of the docking time ratios. In this case, we're running the SYCL version on the Ponte Vecchio or Max 1550, and we're running the CUDA code on the A100. And here, the Max 1550 is faster than the A100 for those plots which are below the horizontal line. And the maximum speedups we achieved was 142 for the case of the solid sweats method and 1.88 for the case of eta delta. So both versions, SYCL and CUDA, are compute bound. However, the expected speed up, if we consider the theoretical performance capabilities of these two devices, is 2.6. However, in reality, we achieve lower speed ups, and we think this is possibly due to an inefficient usage of compute resources, especially on the calls that calculate score and gradients that are intensive ones. So we have used compatibility tool to migrate the CUDA version of Autodoc GPU, and the resulting SYCL code has been reviewed, and we needed to manually modify this, not just to achieve functional correctness, but also to increase the performance of it. Actually, we had to tune the atomics, the barriers, and the math functions in order to use the native ones in SYCL. So these results presented here are, let's say, preliminary, yes, but they are still competitive on CPUs and on GPUs too. So having said that, I would like to thank you for your attention. And if you have any questions, I would be happy to answer. Thank you. Thank you.
Fantastic, thank you. So we do have time for some questions. I actually have one to start with. So how easy did you find it using the porting tool? Was it quite straightforward to use? If you have a complex CUDA code, you can use it to generate SYCL. How much did you have to kind of get involved and change things?
So it was, I would say, it was a smooth experience. Actually, the code comments were quite helpful, actually, that guide me through the migration process. So, yeah.
So it sounds like you'd kind of recommend people actually trying it if they wanted to do something similar?
I would say so, yes. Even the students that we have in our group, they are using it. They only had experience with CUDA, for example, or OpenCL, and they said it was smooth. They didn't have, a steep learning curve. So, yeah.
Great. Cool. Questions? We've got Michael, and then we'll come to Axel.
But did you have to do any hand tuning after the conversion for optimizations?
Yes. So actually, for the barriers, the
barriers and atomics,
and the math functions. Yes.
Okay. Mm-hmm. Thank you.
Thanks. And we've got Axel at the back.
Thanks. So my question is, I think you said that the CUDA thread fence is already covered by the SYCL group barrier, and I'm not sure this is true, because thread fence has a device-wide memory scope, while the group barrier in SYCL by default has a group-wide memory scope. Mm. So wouldn't the correct replacement be a group barrier with the argument of a device-wide memory scope?
Let me see. You mean this in this slide? Right?
No, before. When you were talking about the barriers.
Okay. This one?
Here, a thread, yeah. And here you said that you could replace the thread fence as a no-op.
Okay. There, right?
Yeah, exactly.
Mm-hmm.
Because you already had the barrier. And I think this is not necessarily true. This would only be true if you had a thread fence block.
Okay. Well, we made that transformation just because there were many instances of those thread fence calls in many places in the code, in the SYCL code. So instead of just manually delete them, we just had a macro that replaced them. So it was more for convenience, I would say.
Okay, but then how do you know that the code is still safe?
In which sense?
Well, I mean, if you're removing fencing somewhere, then you could have undesired side effects. But maybe we can discuss.
Yes, it might be a good one to discuss at the break. I don't know if you got the code, or you could see the code on your laptop, but maybe have a look. Thank you. Next one here.
Hello. On your slide about comparing the performance of SYCL versus CUDA on the A100, you mentioned some compiler flag max register count with the NVIDIA compiler. So was that something you did use with the NVIDIA compiler, or is that something you plan to use? And is there an equivalent option you could pass to the back end with the SYCL implementation that you used? Sorry, I just wanted clarification on that.
Okay, yes. Yes, so for the camera-ready version of the paper, we didn't use this, but later in the meantime, we used this and we improved the performance, but it was 5%. So yes, by using this option, we increased 5% of performance of the SYCL version.
The SYCL version?
Yes, 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 yes.
Oh, okay.
So this was just for the SYCL version, yes. Yes.
All right, okay.
Because the CUDA was limiting the number of registers per thread already, but the CUDA was not. The SYCL was not doing that.
Right. Okay. Thank you.
Yep.
And there's another one over this side. Thanks.
Very general question. Have you had the chance to look at power consumptions between the different accelerators, like energy to solution? Any insight on that?
No, actually. No.
Okay, never mind.
Not yet. I'm sure that will come at some point. Good. Great question so far. I've got time for one or two more. Axel's got another one.
Is your code using USM pointers or the buffer accessor model? Because that can potentially have an impact on register pressure.
It's using share memory, yes.
So USM?
USM, yes.
Okay.
And here we go, one at the front.
Yeah, just a question. Since you port it to SYCL, are you planning also to test it on an heterogeneous solution, so CPU plus GPU?
We haven't planned that yet, but maybe.
Yeah, it's interesting actually. So for docking codes, which tend to be compute bound, and we don't find many codes that are compute bound, but docking codes are one of them. It is an area where often you can use the CPU and the GPU at the same time and basically add the performance together. When many codes are memory bandwidth bound, actually if you run on the CPU and the GPU, they tend to interfere with each other and you don't get as much extra performance as you'd hope. But we did that with Butte. We actually ran on the CPU and the GPU with OpenCL and basically added the performance together. You got like an extra 10%, 20% from the CPU. So you might be able to do that. That'd be interesting.